Look at this astonishing image captured by the James Webb Space Telescope. At first glance, it might seem familiar, resembling a magnificent planetary nebula, such as the famous Eye Nebula. Such nebulae represent the final evolutionary stage of medium-mass stars, comparable to our Sun. After reaching the red giant phase, these stars, lacking sufficient mass for a supernova explosion, simply shed their outer layers into interstellar space, forming a bright, expanding bubble of gas. At the heart of such cosmic beauty invariably lies the cooling core of the former star, a white dwarf, slowly fading into the cosmic abyss. However, what is depicted in this image is an entirely different object, capable of overturning conventional notions of stellar evolution. The central star of this nebula is not a white dwarf at all. Instead, we are looking at a true stellar giant, whose mass reaches approximately 30 solar masses. It is not merely cooling slowly but continues to actively and incredibly intensely eject matter into the surrounding space. The star, known as WR124, has already expelled an amount of material equivalent to about 10 times the mass of our Sun into space. Just imagine this cosmic drama. It is literally tearing off chunks of superheated plasma, and this process will not cease until it ultimately explodes in one of the most powerful bursts in the universe, a phenomenal event known as a supernova. This is how Wolf-Rayet stars manifest themselves. These cosmic objects represent an extremely special and incredibly rare class of stars. On average, only one such star can be found among 100 million other stars inhabiting our galaxy. They are not only striking in their colossal size and unimaginable mass but also stand out for their dazzling brightness, often millions of times exceeding the Sun's luminosity. And despite their exceptional rarity, these stars play one of the key roles in the dynamics of matter distribution on a galactic scale. Prepare to encounter the most extreme type of stars, whose nature is both intriguing and awe-inspiring. Our story begins in the mid-19th century. Two distinguished astronomers, Charles Wolf and Wolf-Rayet, conducted studies of stellar spectra using the 40-centimeter telescope at the Paris Observatory. This marked a truly new milestone in the development of astronomy, as light from distant celestial objects began to be broken down into its components, allowing their chemical properties to be determined. Typically, when studying stellar spectra, astronomers observed a similar pattern. At certain wavelengths, radiation was simply absent. These black gaps were nothing less than absorption lines, serving as direct proof that the star's upper layers contained numerous chemical elements capable of absorbing specific wavelengths of stellar radiation. This was the pattern Wolf and Rayet were accustomed to seeing when examining the spectrum of yet another celestial body. However, in the constellation Cygnus, they suddenly discovered three stars that looked completely different, defying all established notions. Instead of the familiar absorption lines created by atoms, the astronomers, to their astonishment, saw additional bright lines in the spectrum, emission lines. Clearly, these are some very unusual stars, Wolf and Rayet thought, but they could not provide any exhaustive explanation for them. For decades, astronomers puzzled over the nature of this mysterious phenomenon. In the early 20th century, Edward Charles Pickering hypothesized that at least some Wolf-Rayet stars might be the central objects of planetary nebulae, as they exhibited similar spectral characteristics. Well, he was only partially correct. To begin with, emission lines appear in the spectrum, oddly enough, precisely because of emission. Various atoms of chemical elements are responsible for this process. They first absorb high-energy photons and then emit them. By absorbing photons of a certain wavelength, they transition to a higher energy level. Atoms cannot remain in such an excited state for long, so in a matter of micro or nanoseconds, they return to their lowest, ground energy level. This transition releases excess energy in the form of a photon of a specific wavelength. These are the photons astronomers see in spectra as emission lines. In general, by their nature, emission lines are usually very narrow, somewhere within 1 nanometer. However, in the spectra of Wolf-Rayet stars, the lines, conversely, turn out to be unusually broad. There are several reasons for their broadening. Some are purely quantum mechanical, due to the very nature of fundamental particles, which always possess a certain uncertainty in their basic parameters. However, Other reasons are directly related to motion. If we imagine that atoms emitting photons move at different speeds relative to the observer and their telescope, then due to the Doppler effect, these photons will arrive with different wavelengths. For example, imagine a black hole's accretion disk, where matter in one case moves towards you and in another, away from you. Those atoms moving in your direction will exhibit a blue shift, meaning their emission wavelength will decrease, while those moving away from you will have a redshift, and the wavelength will increase. Thus, photons from the same source will generally arrive with different energies, meaning different wavelengths. In the spectrum, this will manifest not as a narrow emission line but as a broad band that will cover a significantly larger, expanded range of wavelengths. In the first half of the 20th century, astronomers finally grasped this principle. And, as if by magic, the spectrum of Wolf-Rayet stars revealed its true nature. Scientists realized that the matter emitting photons was being ejected by the star in all directions at incredibly high speeds, on the order of hundreds, and sometimes even several thousands of kilometers per second. This, incidentally, already constitutes several percent of the speed of light. So, what kind of stars are capable of producing something like this? For this, one should look at the well-known Hertzsprung-Russell diagram in astronomy, where different types of stars are arranged based on their temperature and color. The most prominent and longest band here corresponds to the main sequence. As a reminder, this is a key stage in the life of any star when it still has enough hydrogen for nuclear fusion. It's like a mature age, when it can shine peacefully without disturbing the cosmic balance. In the lower right part of the Hertzsprung-Russell diagram, on the main sequence band, traditionally lie cool and relatively dim red dwarfs. As an observer moves up and to the left across this diagram, they discover stars that become increasingly brighter and hotter. Passing through the region where our Sun is located, one can notice how stars acquire an increasingly pronounced white, and then blue, hue, which directly indicates an increase in their temperature. Ultimately, in the upper left corner, at the very boundary of stellar possibilities, are the hottest and most luminous stars. These include O-type spectral class stars, colossal blue-white giants whose typical masses range from 15 to 80 solar masses, and surface temperatures exceed 30,000 Kelvin. For comparison, our Sun's photosphere has a temperature of about 5,500 Kelvin. These stars are unusually massive, which is an inherent characteristic for main sequence objects. The greater a star's mass, the higher its temperature. However, the life cycle of such stars is extremely short, typically no more than 10 million years. This is why they are most often observed in regions of active star formation. They are responsible for the spectacular blue-white glow characteristic of galactic spiral arms. Nevertheless, despite their striking prominence in the galactic disk, O-type spectral class stars are extremely rare. Such is the nature of physical processes that it is much more difficult for gas clouds to collapse into a single star whose mass, for example, is 30 times that of the Sun. A much more likely scenario is the fragmentation of the cloud into many parts, leading to the formation of numerous smaller stars. If you add their short lifespan to this, it becomes clear why there are no more than a few tens of thousands of such stars in our galaxy, while the total number of other stars exceeds 100 billion. Wolf-Rayet stars, however, represent an even greater rarity, as they are believed to be one of the possible evolutionary paths for blue-white giants. Let's imagine a star whose mass exceeds 25 solar masses, and which is still in the main sequence stage. As already noted, such stars are extremely hot. Their temperature is measured in tens of thousands of Kelvin. This factor is precisely what causes powerful stellar winds. Indeed, even during the relatively calm stage of hydrogen thermonuclear fusion, these stars lose significant amounts of matter. Under the influence of such a stellar wind, they can lose up to 2 Earth masses annually. It is worth noting that mass loss is a common feature for all stars. For example, our Sun can eject 1 Earth mass into space in approximately 45 million years. However, there is a direct correlation. The hotter a star is, the more intensely mass loss occurs. This is explained by the fact that higher temperatures mean photons carry greater energy. When these high-energy photons are absorbed by free ions in the star's upper layers, they impart significant momentum to them. Simply put, high-energy photons literally collide with free ions, and the imparted momentum pushes the matter outward. Essentially, radiation creates pressure that physically pushes matter into space. This phenomenon is stellar wind. But the true cosmic hurricane erupts in the final stages of blue-white giants' lives. Upon leaving the main sequence, the star burns through the last reserves of hydrogen in its core. At this critical moment, the star loses its ability to maintain stable upward pressure from gas and radiation. As a result, the star's own gravity begins to prevail. The dominance of gravity leads to the star's compression, and compression, as is known, always leads to an increase in internal temperature. Thus, the core heats up even more, initiating helium burning. The outer layers of the star gradually blow away, exposing the inner, significantly hotter regions. The surface temperature also increases by orders of magnitude, reaching 90,000 Kelvin, and sometimes even higher. As previously established, an increase in temperature increases the energy of radiation, which causes stellar winds to blow at incredible speeds, reaching 2,000 to 3,000 kilometers per second. This is how a Wolf-Rayet star is born. At this stage, the radiation pressure becomes truly colossal, 3 to 4 times exceeding the typical stellar wind of O-type stars. In physics, there is a certain luminosity limit for a star, beyond which radiation can literally tear it apart. This phenomenon is known as the Eddington limit. The hurricanes characteristic of Wolf-Rayet stars already bring the star very close to this limit, forcing the surface layers to literally detach from the star under the influence of this continuous, incandescent glow. It's hard to even imagine such brightness capable of producing something like this. Sometimes this is indeed called a solar hurricane. But any analogies with our sun, of course, cannot convey the true scale of the phenomenon. Imagine a gentle breeze on a calm day compared to a powerful stream of water from a fire hose. The difference is truly impressive. Wolf-Rayet stars generate winds that are 10,000 times more powerful than solar winds. Naturally, the mass loss in this process becomes simply colossal. In just 100,000 years, even a not-so-massive Wolf-Rayet star can lose a mass equivalent to our Sunday 100,000 years. By cosmic standards, is practically an instant. It is believed that in this extremely short evolutionary stage, which can last only a few 100,000 years, stars can lose 50 to 90% of their initial mass. Thus, a typical O-type star with an initial mass of 30 solar masses can weigh 10 to 15 solar masses by the end of the Wolf-Rayet stage. It's astonishing how much matter it ejects into space. Obviously, to maintain such high temperatures and luminosity, stars consume their thermonuclear fuel incredibly quickly. And this stage of their evolution only accelerates their destructive demise. Stars with masses up to 100 suns usually end their lives in supernova explosions, presumably type Ib and Ic. Some are expected to turn into hypernovae, which are like supernovae, but on steroids. However, stars with masses from 130 to 250 solar masses can even explode as parent stability supernovae. This event is particularly destructive, as it completely tears apart the entire star, leaving behind neither a neutron star nor a black hole. Remarkably, the spectra of Wolf-Rayet stars bewildered astronomers of past eras not only because of their broad emission lines. These spectra practically lacked hydrogen, which, as is known, did not conform to the usual notions of superheated hydrogen-helium spheres. However, Wolf-Rayet stars are naked stars. They actively shed their hydrogen envelope, exposing internal depths rich in helium. Essentially, researchers are observing a stellar core that, in addition to helium, also contains carbon and other heavy elements synthesized by the star throughout its relatively short existence. Therefore, the classification of such objects is usually based on their chemical composition. In the spectra of some, ionized helium and nitrogen dominate. Such stars are designated as WN. In the spectra of others, ionized helium, carbon, and oxygen dominate. They are marked as WC. In exceptional cases, oxygen may prevail over carbon, so such stars are classified separately as WO. In any case, the presence of all these heavy chemical elements in the spectrum heralds the star's rapid approach to its brilliant end. But before completing their life cycle, Wolf-Rayet stars are capable of producing truly unique astronomical phenomena. They are not only striking in their impressive beauty, but also perform a key function in their galaxies. First and foremost, by releasing energy into interstellar space, stellar winds compress the surrounding gas. This, undoubtedly, is a powerful stimulus for the process of star formation. In certain cases, they form spherical nebulae, picturesque cosmic bubbles, a vivid example of which is WR31A. This bubble is about 20,000 years old, and is steadily increasing in size at a speed of 60 kilometers per second. Yet, the most significant contribution that such stars make to their galaxies is stellar dust. Since after shedding its hydrogen envelope, the star does not stop and continues to eject matter, various heavy chemical elements are expelled into interstellar space, which can condense into dust grains. In general, dust is exceptionally important for the cycle of matter in a galaxy. Due to its property of absorbing and scattering ultraviolet radiation, dust creates a natural barrier, darkening molecular hydrogen clouds. This protects molecules from the destructive influence of harsh radiation that can destroy them. Dust also helps gas clouds dissipate heat more effectively. It absorbs energy from colliding atoms and molecules and emits it into space in the form of infrared waves. It is vital for gas clouds to cool. This promotes their more intense compression and eventual gravitational collapse into protostars. Thus, for star formation, the significance of dust is invaluable. And this is in addition to the fact that objects like planets are born from dust particles. Moreover, they can contain organic molecules. And quite literally, we ourselves originated from cosmic dust. In astrophysics, there has always been an unresolved problem in explaining the colossal volume of dust present in galaxies, including our own. Its quantity is disproportionately large. One of the potential sources of this dust that scientists consider is precisely Wolf-Rayet stars. For example, consider the phenomenal system known as WR140. At its center is a Wolf-Rayet star, and surrounding it is a cluster of interstellar dust that the James Webb Space Telescope was able to capture. At first glance, all these streaks might be perceived as some kind of optical distortion of the image, but it should be noted that this is a genuine natural phenomenon formed by dust. In fact, even more paradoxical is the very presence of dust so close to the star. The thing is, in astrophysics, dust can be compared to snow. There's a lot of it in a calm, cool climate, but certainly not near such extremely hot, high-energy objects as Wolf-Rayet stars. That is, even when ejecting carbon, oxygen, or nitrogen into space, dust cannot concentrate near such stars because the temperature regime here is excessively high. So how to explain its presence in this image, and in such a peculiar structure? The whole secret lies in the fact that WR140 is not a single star. It is a binary star system, where another O-type blue giant orbits alongside the Wolf-Rayet star. In the 1980s, astronomers discovered that the dust rings directly correlated with the 8-year orbital period of this pair around their common center of mass. Therefore, scientists hypothesized that dust forms at the moment of the pair's closest approach to each other. As is known, even main-sequence blue giants are characterized by powerful stellar winds. Thus, during the star's close approach, their winds must collide with each other. Crashing into one another, the streams of matter lose speed and gradually reduce their temperature. Eventually, conditions can become optimal for the process of dust and gas condensation. Thus, with each orbit of the pair, a new dust shell appears, enveloping the stellar bodies like layers of an onion. There are other fascinating configurations that dust forms. For example, the binary, and possibly triple, system WR104 forms a spiral shape. The two main stars, one of which is a Wolf-Rayet and the other an OB-type blue-white giant, orbit at a distance of only 2 astronomical units from each other. For reference, this is comparable to the distance from the Sun to the main asteroid belt. Therefore, the pair completes a full cycle around their common center of mass in just 240 Earth days, which is about 8 months. Consequently, astronomers can observe and analyze the system's dynamics almost in real time. The spiral dust trail observed in such objects apparently arises from the same dynamic processes as the characteristic shells of star WR140. This refers to the powerful interaction of stellar winds emanating from the system's components. As the system rotates, the ejected dust gradually expands outward, forming a distinct spiral shape. Similar spiral formations have been discovered in other systems involving Wolf-Rayet stars. As a result, astronomers have grouped them into a special category called pinwheels. Notably, in 2008, the WR104 system attracted significant public attention. Researchers, in describing its physical characteristics, carelessly mentioned the potential threat it could pose to our planet. It is worth noting that during that period, humanity did not have an abundance of real reasons to worry about the end of the world, and so people readily found them on their own, for example, in ancient Mayan prophecies pointing to 2012. Thus, when scientists in their scientific publication briefly mentioned the non-zero chances of a gamma-ray burst occurring in this system, it literally provoked a storm on the internet. Indeed, giant stars are considered potential candidates for such powerful gamma-ray bursts. However, not all of them are capable of realizing such a scenario. Typically, this is expected from stars that possess rapid rotation. During the collapse of a star's core and the subsequent formation of a black hole, it is rapid rotation that allows an accretion disk to form even before the entire mass of the star is consumed. The presence of an accretion disk becomes the condition for the emergence of powerful jets of matter that are ejected from the black hole's poles. These jets penetrate the still existing body of the star and, erupting into space, manifest as intense gamma radiation. Stars that rotate slowly, on the other hand, are usually unable to form an accretion disk and explode as regular supernovae, without a gamma-ray burst phase. In the case of the WR104 system, it so happens that both of its main stars apparently possess sufficiently high rotation speeds. Although precise data is lacking, models of their dust tail and the presumed interaction between the components indicate this. Moreover, previous observations have shown that the poles of the stellar pair may be oriented directly towards Earth, and the system itself is located at a distance of 8,400 light-years, which is relatively close by cosmic standards. Therefore, the authors of the study cautiously suggested that a potential gamma-ray burst from this system could indeed pose a danger to our planet. Nevertheless, despite all the resonance it caused, there is effectively no real cause for concern. First, the probability that the relevant Wolf-Rayet star or its companion will undergo a gamma-ray burst phase before exploding as a supernova is extremely low. Such events are most often observed in galaxies with low metallicity, which certainly cannot be said about the Milky Way. Of course, this does not exclude the threat from the supernova itself, as the main energy of the outburst is also directed along the star's poles. However, later studies demonstrated that both stars in the WR104 system actually have a certain tilt relative to the plane of the dust cocoon. According to current estimates, this angle is between 30 and 40 degrees. Consequently, it is unlikely that a gamma-ray burst or supernova from this system could threaten our planet, as their radiation simply would not reach Earth. Everyone concerned about this issue can breathe a sigh of relief. Except, of course, for astrophysicists, who still need to understand why the stars and the dust spiral do not rotate in the same plane. In general, Wolf-Rayet stars, unfortunately, are still shrouded in many mysteries. For example, astronomers still do not sufficiently understand their internal structure and how it transforms throughout their evolution. The role of magnetic fields in all these turbulent processes is also not fully clear, and measuring them is an extremely difficult task. The main problem lies in the data deficit, which is due to the small number of Wolf-Rayet stars themselves in our galaxy. Currently, about 700 such stars are known in the Milky Way, although estimates suggest their total number here does not exceed 1,000. Given their extremely short lifespan, only 200,000 to 500,000 years, it is not surprising that there are so few of them in our galaxy. In fact, only 2 of them are visible to the naked eye, and both, unfortunately, are true gems of the southern sky. The most famous and simultaneously the brightest of them is named Gamma Velorum and is located in the constellation of the same name. It is one of the brightest stars in the southern hemisphere, although it is essentially not a single star but a quadruple system, among whose components a Wolf-Rayet star is present. However, most of the system's brightness comes not from it, but from its O-type spectral class neighbor. It's often observed that blue-white giants are frequent companions to Wolf-Rayet stars. Indeed, all of them originate in dense star clusters and frequently form binary systems. Many other candidate Wolf-Rayet stars have been discovered by astronomers beyond our galaxy. There are even entire Wolf-Rayet galaxies, a phenomenon where these stars are so numerous that their characteristic spectral lines begin to dominate the overall spectrum of the entire galaxy. Astronomers have also found between 150 and 200 Wolf-Rayet stars in each of our large galactic neighbors, specifically in the Andromeda Galaxy, the Triangulum Galaxy, and of course, the Large Magellanic Cloud. It is there, in the local group's largest star-forming region known as the Tarantula Nebula, that the largest, most massive, and brightest known star, our 136A1, resides. This cosmic titan is approximately 200 times more massive than the Sun and emits light over 6 million times brighter. Yes, it is indeed a Wolf-Rayet star. Annually, it loses mass equivalent to 22 Earths. In just 5 seconds, it emits as much energy as our Sun produces in an entire year. Astronomers therefore believe that, at the beginning of its evolution, this star may have been up to 300 times more massive than the Sun. The question of how such cosmic behemoths can even form poses a distinct and highly complex problem for astrophysics. The prevailing theory states that, generally, stars do not form with a mass exceeding 150 solar masses. This limitation is explained by the Eddington limit, which describes the equilibrium between gravity and radiation pressure. Stars attempting to exceed this threshold would encounter colossal radiation pressure, capable of literally blowing away the remaining protostellar material into interstellar space. Consequently, it is highly probable that stars possessing such impressive mass do not originate directly from gas and dust clouds. Instead, they are most likely the result of a grand merger of two less massive, yet still extremely massive stars. Indeed, celestial bodies are capable of coalescing into a single entity, giving rise to truly gigantic cosmic objects. In common perception, stars like the famous Betelgeuse are often considered true stellar titans, primarily due to their colossal physical size. However, despite these red supergiants indeed surpassing blue-white giants in volume, their actual mass averages only about 10 solar masses. Essentially, they are massive stars characterized by an expansive, highly inflated atmosphere and a relatively low surface temperature, significantly cooler than that of our Sun. Thus, the most massive Wolf-Rayet stars can rightfully be considered leaders among the most extreme, and consequently, most astonishing celestial bodies in the entire universe. Beyond their exceptional nature, they perform a significant function in the life of a galaxy, especially in star formation processes, by influencing the chemical composition of the interstellar medium and stimulating the formation of new generations of stars. Consequently, their comprehensive and in-depth study represents an extremely promising direction in modern stellar astrophysics.